Hi, my name is Katarzyna Michalowska, and I'm a researcher at CENTAF in a group of artificial intelligence and analytics. And I'm also a PhD student at the University of Oslo in informed machine learning. And today I want to tell you a story on how we developed a condition monitoring algorithm for maritime thrusters. And I will mention some challenges that we encountered. And I hope that if you come across similar problems, what I will tell you today will become useful to you in some way. So the problem that we tried to address was monitoring of maritime systems. And these systems, like any types of machinery, sometimes encounter some problems, which then, in this case, can lead to some costly consequences. So, for instance, leakage of lubrication oil in the thrusters, so in this machinery which allows the vessel to speed up and to make turns, leads to overheating of it, the premature wear of this equipment, and then results in the need of replacement of the thrusters. And we hope that by looking at how the thrusters operate, we will be able to see some symptoms of something wrong happening inside of it. And we want to have an early detection algorithm to not have these costs in the future. So why would we use machine learning for that? Actually, the system that we have in our use case is already equipped with some alarms and some other monitoring system. However, this one is very simple. It is based on rules. If the values returned by the sensors that are installed on the thrusters exceed some value, there might be some alarm triggered and so on. However, in the thrusters, there might be only some small deviations, which will be not seen by these algorithms. And also, these are tuned to detect some particular things that we know that can happen in a thruster. So there's nothing unforeseen, really, that we can detect with these methods. So our hope is that by using the flexibility of machine learning, we will be able to actually extract some patterns that wouldn't be so obvious for a human to program. And in this way, detect all wide range of deviations, including the small ones and the ones that we cannot really foresee. So that should be easy. We take the machine learning algorithm and we wanted to extract some patterns. However, in our case, we are lacking some information to make it work. So, for instance, we do not know when the anomalies happened, or even if they happened at all in our thrusters. So we cannot use supervised learning, in which we should have some labels, in this case, the timestamp of this undesired behavior occurring. So the natural thing to do would be to use unsupervised learning. But we actually do not know what exactly we're looking for yet, because here we would have to focus on engineering some features that would be indicative of abnormal behavior, or would allow us to discern this abnormal behavior from the normal one. We don't know how to do that yet, so we cannot use it straight away. I think that is tempting to do could be to use deep learning to learn these features. But if we think about the faults of the thrusters, if the thruster is not working properly, the anomalies could be repetitive in it. And then a deep learning algorithm, which would belong to this semi-supervised category here, would actually run into a risk of assuming that what it's seeing, because it gets repeated, is a normal behavior. And we would miss a lot of anomalies in it. So how to solve this problem? In this case, we decided to mix the paradigms. So we mixed the unsupervised learning with sort of a supervised learning. And then we came up with the anomaly detection algorithm. So first we use the unsupervised learning to discover some initial anomalies, and this way learn about what are we looking for. And then when we have actually discovered some anomalies, we use them to tune our algorithm once it's been trained on the normal or almost normal data. So this is the process that I will guide you through and tell you how we did that. Starting from the beginning, the data that we had was provided by our partner, Brunvoll, who is a provider of these marine systems. So we had actually quite a lot of data, some 4 years of different variables that described the behavior of thrusters located on different ships, and they were expressing different properties like the values of thrust in the thruster, the pitch, you don't need to know what it is for now, the drive motor load, the oil temperatures, and so on. But what we have noticed is that, well, not all of this data was of a very good quality. So we couldn't actually use all of these variables to train the algorithm. Also, we knew that not every thruster has the same set of sensors installed. So when we deploy the algorithm, not all of it would be available. So actually, in the final algorithm, we could also focus on the variable called pitch. A pitch is the distance of the propeller. It's the distance that the propeller would travel forward in one of its rotation, and it's dependent on the angle that the blades of the propeller take. Here we can control it because we have a controllable pitch propeller, and it is controlled by a simple logic. In here, a set point is given, so the desired pitch of the propeller is given to the controller, which then sends a command to open a valve, after which the pressure changes, adjust the pitch, so they adjust the angle of the blades to the desired angle. After that, the sensors detect it or measure it and send it back to the controller. This loop repeats. So what we want to see here is in the data is that when the set point changes, in this plot it's the yellow line, the command is given for the feedback to change, and after that the feedback changes to meet the set point. We want this interaction to work like this, and this interaction is what we want to focus on to describe the normal behavior. But we need to find out how to actually describe it. And to do that, the first thing we want to do is to find some anomalies to help to discern this anomalous behavior from the normal one. And again, we did that in sort of a loop. We first transformed our data. After that, we applied some unsupervised learning methods on it, in which we could detect some outliers. Then we went manually into each and every one outlier and verify whether it was an anomaly or not, and labeled them. After we have some set of labeled anomalies, we could kind of reverse it and see what features that we used were actually indicating these anomalies. After that, we could take the features all together, or only use the ones that were indicative of the anomalies and ignore the other ones, make another data transformations, train the unsupervised learning algorithm again, detect outliers, and so on. So here we have some tips. First of all, it might be tempting to just use the data that will be available in deployment, because we already know that we cannot use all the other variables. But actually, we have all the features, also these noisy ones. And it might be easier to detect some things using these features. So for instance, we have noticed that it's very easy to detect some anomalies by looking at the drive motor load of the thruster and its servo pressures. We have noticed that if the drive motor load was high and the servo pressures were low, which here are clear outliers, the pitch was not following the set point as good as we could. So that gave us a label on these points which were anomalous there in a much easier manner. In that, it needs to be mentioned that it's also always great to contact your experts and ask them about what do they think should be used to detect some anomalous behaviors. The next thing we did was actually to describe these time series that we had in some different manners. So for that, we used an automated feature extraction using some libraries in Python. First of all, we divided the data into smaller periods of 5-minute intervals. And then we used these libraries to automatically extract very many features, over 2,000 features. Of course, this is too much data to analyze anything on it. It's good that it happens automatically, but it doesn't give us anything. It's still a lot of work. So then we used the dimensionality reduction techniques, which kind of made more sense about this data for us. In this way, we were able to label more and more anomalies in different settings. Here's an example of one of them. And that gave us some more labels and some more anomalies to look at. And so once we have repeated these processes, we could look. We weren't quite done with the old 2,000 features that we have created, right? So we wanted to find out which of them were actually indicative of our anomalous behaviors. So to do that, we compared the distributions. We took our data and we divided them into samples. The first one was the normal behavior and some anomalies that were hiding in it, but we haven't found them yet, and our already found anomalies. These two groups, we have derived the distributions for each feature on these samples, and then automating that process with some statistical tests, we have found which of the features were indicative. In this previous loop, we can also just use these features that were indicative, retrain the unsupervised algorithm, detect outliers, and so on. It's the same process. An example that we used was the Kolmogorov-Smirnov test, in which the assumption is that these two samples have came from the same distribution. And if this is not satisfied, we look at the p-values. If they are high, it means that we can take that feature and it might be indicative of it. So after this process, we ended up with quite many anomalies. We have found almost 100 of them, and we could roughly divide them into 5 groups. So the first one was the compensating command, in which the command given to move the blades was relatively high to achieve the same change in the pitch. The second one was unreactive command, when although the feedback was deviating from the desired pitch, so the set point, no command was given, and so nothing was reacting to it. The pitch was not adjusting. After that, the third one was to detect sensor issues, in which the feedback, so the measured value of the pitch, was actually changing so fast that it's not feasible physically, because this is a physical process to adjust these blades. Another one was the pitch being adjusted with a delay, so things were working a bit slower than they should be. And the last group was when the set point has changed. The command was given to change the actual pitch, but nothing was happening. So we call that unreactive feedback or unreactive pitch. So having these anomalies, we now could train our actual algorithm. And so the algorithm was a semi-supervised learning group that we named it this way. Yes, and in this process, we also had In this process, we also had the loop through which we were going. So first, we applied some data transformations, and in this case, we only used these variables that would be available in the deployment. So we are already trying to make our final algorithm. We trained the model, and then how do we compare the models between each other? Or how do we tune such model if we actually cannot use the actual supervised learning in it? We only have some proportion of the anomalies. So that was the third phase, to which I will explain later, in which we tuned the algorithm. After the algorithm has been tuned to detect the anomalies that we have found, we contacted our experts in Brunvo, and we were asking them, okay, do you think these features that we are using are general enough to actually find some wider range of anomalies, or is it just some overfitting of these particular anomalies that we have found? So by doing this loop, we made sure that our algorithm was general enough to find a wide range of deviations, but also was able to find all the anomalies that we knew that were in the data. To be able to find this wide range of deviations, we also trained a model that was a one-class classifier. In this, this one class is the normal behavior, and anything that is outside of it is deemed an potential anomaly. So this is in contrast to training an algorithm which will be focused on detecting particular anomalies and recognizing this behavior that would be anomalous. Anything that would be outside of what we describe as the normal behavior would be deemed as anomalous. So in this, we had to make sure that our features that we use actually capture the interactions that indicate the normality or abnormality of this behavior. And we also didn't want to include irrelevant information, because in that we would only end up, for instance, dividing the data into some more usual modes of operation and some less usual modes. So we didn't want the algorithm to focus on that and just give us a lot of false positives in this. Okay, so how do you compare your models if you only have few labels? Here we use the traditional measures that are typically used in classification. So precision, it is a measure of how many true detections. So this okay. Let me just have a pen. Yeah. So here, the true positives are in this circle. So precision is a measure of how many of these true detections there were in all of the instances that the algorithm thought were anomalous. So the algorithm gives us many anomalies, and then we look at how many of them were actually the anomalies. Then we use the recall, which says how many of all anomalies that we have in the data that should have been detected by the algorithm were detected by the algorithm. So in the idealist scenario, we would want to, okay, I thought that you were seeing my pen, but I need a laser pointer for that. Okay, so in perfect conditions, we would want the precision to be as high as possible and the recall to be as high as possible. And then a random guessing of, okay, what class could it be for the precision would be equal to the ratio of positive samples, so the actual anomalies, with respect to all of our data. So for instance, if 33% of the data was anomalous, this line would go here. This would be random. So in our case, we actually want to focus, or we want to have a high recall, because we want to make sure that our algorithm is picking out on all of these anomalies that we already know that there exist. But because we are also aware that in our labeled data, there are some anomalies hiding, probably, we want the precision to be a bit lower. So in every iteration of the tuning, we would look at the model and look at the models and pick the ones with high recall and slightly lower precision, and look if any of the outliers that they are detecting are actually anomalies. Actually, even in the deployment, it might be good to stay with this lower precision. It's better to detect too many of the anomalies rather than miss some of them. So the lower precision would allow us to detect actually these cases in which the algorithm is kind of unsure whether it's an anomaly or not. And so we might get some unusual samples that are not anomalies, and they will be false positives. But how we work on it and how we analyze whether there's a problem in thrusters is actually done on a larger timescale basis. So in this case, we would look at a particular thruster, and we would see how many detections have there been in some period. If there have been 2 detections in 1 month, and then in the other month there would nothing really happened, that will not be a reason for our concern. But if we saw an increasing number of the anomalies, or there were particularly many anomalies, then we would be worried. So we can still have this lower precision that will sometimes give an occasional false positive, and still analyze the data afterwards in a manner that will tell us whether we should be concerned or not. So now I will give you an example, or I will tell you that what were the features that we created in our use case. So first of all, we tried to model the feedback, that is the dotted line, based on the commands given to change that feedback, because that should be possible, right? Given the value of the feedback that there is now, the command is given to move it, and we can adjust it. We did that using a simple linear regression, which was good enough for the model to work. And then we compared this expected feedback or expected pitch with the measured pitch. If the deviation was larger than minimal, that would indicate that there is some problem. So in the final algorithm, we used 4 features. 2 were the errors between one variable and another. So the first one was the error between this measured and expected pitch. The other one was the error between the measured pitch and the set point of the pitch. And then the other one was the longest time interval in which this deviation between the measured pitch and the desired set point was larger than some value, which was typically a deadband for the thruster. So the difference between set point and feedback, in which the thruster will say, okay, this is good enough, and not correct itself. And then the last thing was the maximal change in pitch feedback, in which, okay, so if something changed too quickly, it means that there might have been a sensor problem in place. But in our data, we still didn't know if there was any leakage. So how do we test that? We didn't know how to test that. So we just called people on the ship, and we asked them to make a physical simulation for us. What they did was to open a valve and actually make a physical leakage to a thruster while it was operating, but in some safe conditions. And we could see that when they were opening the valve and the oil was flowing into the thruster and there was this leakage, the algorithm picked up on it very quickly. And then when they were opening it more and more and more, the alarms also picked up on it. But that was a bit late. So obviously in the real world situation, this leakage would not happen so fast. So actually we could say that our algorithm was able to detect this leakage much, much sooner than these alarms would react. So that was very good. And it showed in our data by the expected feedback, which should be following these other lines, going crazy. So yes, So by the commands given, the feedback should be changing so much, but because the thruster was already fluted, it was changing slower. This small program or algorithm was a part of a larger project called FAST, which is in Norwegian, but it means Business Models and Advanced Sensor-Based Condition Control. I will not try to say this name in Norwegian. And it's a project that has been running since 2019, and we will still be working on it for over a year. It's a collaboration between SINTEF, Sperre Industri, and Brunvoll. And our project goal is to develop an expert system for condition control of equipment supplied by Brunvoll and Sperre. And the system would be much larger. So where we are is now onshore. The whole system would be comprised of offshore and onshore applications, in which the offshore, so the one located at the vessels, applications monitor the thruster there. Then the data about it gets sent through the internet through a secure connection and lands at Brunvoll's monitoring center. Our algorithm is right now running here, but it is also lightweight enough to, in the future, maybe be running on the vessels. We don't know if we want that yet. Another part of this system is that all the analytics made about the vessels are sent by Brunvoll to the ship owner dashboards. So this is the larger perspective of that. And then, summing up our very small project, very small algorithm, we have got some maritime systems that were equipped with sensors and already had some alarms in place, but we thought that they were insufficient. We wanted to detect a wider range of anomalies and to do it early to not suffer these consequences. So we tried machine learning and we succeeded, but it was not so straightforward. And to do that, we had a mixture of different machine learning paradigms and domain knowledge from our experts, and we solved this problem. So I guess the conclusion is to never give up and try many things when they don't work, and don't believe that you can't use your machine learning algorithm. And thank you. That will be it.